Okay, so this session is based on the, or will be based on the Cobb-Douglas production function. So of course we have different types of production functions, but today we are going to concentrate on the Cobb-Douglas production function. I think we had some bit of introduction to this production function when we were introducing the macroeconomics. Okay, so we said the Cobb-Douglas function, just like any other production function, defines the relationship between inputs and output. But in this case, the only difference or the main distinguishing factor of this particular production function is that it shows us the proportion of output that goes to each factor of production. Okay, it shows us the total output that goes to each factor of production. Of course, you will not get this property from any other production function except the Cobb-Douglas production function. So the Cobb-Douglas production function is able to tell us the proportion of total output or total income that goes to each factor of production. And then I believe we know what factors of production are. Okay, in this case, we only have two: capital and labor. Okay, capital and labor. Okay, so basically that's what we're going to be looking at in today's discussion. Okay, so we are saying that this thing called the Cobb-Douglas production function is one of the most important production functions in economics. Okay, so this production function is of the form of this, it's of this nature. Output Y is defined to be equal to A times capital raised to the power alpha times L raised to the power 1 minus alpha. So whenever you find something of this nature, either in mathematics or in economics, this thing represents the Cobb-Douglas production function. Okay, so Y represents the level of output. Okay, A represents the level of technology, K is capital, L is labor. Alpha shows us the proportion of income that is paid to capital. 1 less alpha shows us the proportion of income paid to labor. Okay, so that's the interpretation of the Cobb-Douglas production function. Okay, so that's the interpretation. What's the name again? Okay, so that is the interpretation of the Cobb-Douglas production function. Okay. Okay, so that is the interpretation. So the interpretation is that this A is the level of technology, okay, or technological advancement. K is capital. Then A alpha, okay, alpha, this is not A, it's alpha. Alpha represents the proportion of total output that is paid to capital. And then 1 less alpha is the proportion of output that is paid to labor. Okay, so anything of this nature represents the Cobb-Douglas production function. Okay, so anything of that nature represents the Cobb-Douglas production function. Okay, now we are saying that let me just admit. Okay, so today we are just a bit strict. We're trying to to avoid this whole thing. I believe you know what I'm talking about. So the paid up members should enjoy their their monies that they paid. So that's the protocol we're using today. Okay, so who is that? Okay. So let's continue. Sorry, let's continue. So we're saying where A is a parameter greater than 0 that measures the productivity of technology. Alpha is the share of income that goes to capital. 1 less alpha is the share of income that goes to labor. Okay, of course, Y is the total output. Thus, we have output Y being the function of capital and labor must equal AK alpha labor 1 less alpha. So this is the Cobb-Douglas production function. So this is the Cobb-Douglas production function. Okay, so this is the form of the Cobb-Douglas production function. So of course you'll be given what A is, you'll be given what K is, you also be given what L is. Okay. Okay. So this is how the Cobb-Douglas production function is defined. Okay, or this is the general form of the Cobb-Douglas production function. Christopher, how is my audio?
We can get to Mr. George. You're audible enough.
All right, thank you so much. Okay, so let's now look at the properties of the production of this production function. Okay, let's look at the properties of the Cobb-Douglas production function. So the first property is that it exhibits constant returns to scale. Now, I think by now we understand what it means when we say, this economic variable exhibits constant returns to scale. Because we know that this is, or that is, if the inputs, in this case capital and labor, are increased by some amount, okay, or by the same proportion, then output will also increase by the same proportion. Okay, so today, as I've already said, we are looking at the practical side, not the theoretical side, because today we are trying to prove these assumptions. Okay, we are trying to prove these assumptions. So the first assumption that we are going to prove is this very assumption that the Cobb-Douglas production function exhibits constant returns to scale. We have to prove this mathematically today. Okay, so we know what exhibiting constant returns to scale mean, because it means that if we increase inputs, let's say by 10, then output will also increase by that same value 10. Okay, if after increasing if after increasing inputs by 10, output only increases by 5, then you have got diminishing returns to scale. Okay, and then again, if you increase inputs by 10 and then output increases by, let's say, 30, then you have got increasing returns to scale. But in this case, we are assuming that the Cobb-Douglas production function has got constant returns to scale, meaning that if we increase inputs by any amount, let's say Z, then output must also increase by Z. Okay, so you're saying this is the production function. This is the production function. If inputs are increased by Z, okay, some quote Z, then we're saying if we plug in Z, which means we are now increasing capital and labor by Z. Okay, that's why I've got the function of Z capital, comma, Z labor, which means we have increased the inputs by an amount Z. Then output must also increase by this Z. Then we are going to conclude that the production function exhibits constant returns to scale. So Z can be any other number. It could be 2, it could be 1, it could be 3. Okay, so Z is any number that you may think of. Okay, is represented by Z. Okay, so if we increase capital by Z, labor by Z, then let's plug in Z here now. So we're going to say A, open brackets, we have increased capital by Z, so which means Z times capital, close, raise the power alpha. Why? Because capital is raised to the power alpha. Okay, again, Z times L, everything raised to the power 1 less alpha. Why? Because L is raised to the power 1 less alpha. Okay, now let's open the brackets. So I've got A Z raised to the power alpha, because Z will be raised to the power alpha, okay, because we're multiplying everything by that very power. Then K should also be raised to the power alpha, because this alpha is applying to everything in the bracket. Okay, then so we are now this side. Z should also be raised to the power 1 less alpha. L should also be raised to the power 1 less alpha. So now we have opened the brackets. But of course, our aim is to prove that this production function exhibits constant returns to scale. Okay, that is our aim. Okay, so now let's bring the like terms together. So we are saying that the function of Z capital Z labor must equal, now these guys raised to the power alpha, like the Z's must come together same side, and then in the production function this guy should also be collected together. Yes.
Excuse me.
Yes.
Hello.
Yes, I can get you. Who was on the floor? Someone wanted to say something?
Yes, it's Mary. Now she seems to be having some network
Just start again, because I'm not getting what you are doing or saying there.
Could that be my net or her net? That's
Kindly repeat. I'm not
It's a
getting
network.
what you are saying. Like from the start, I'm seeing you explaining Z.
Oh, okay. But wait, before we do that, Mary, are you able to get me clearly? Miss Mbozi, are you able to get me clearly now? Hello? Mary, just respond, please.
Mr. George, she seems to be having some network challenges.
Okay, if that is the case, the session is being recorded. Okay? So, let us not worry.
So I'm saying that you should be... wait.
Okay.
You are breaking.
Okay, but I believe it's your network. It's not my net, because I think my net is full. Like I'm having 100% net.
Okay, yeah, I'm about to hear you. But
okay, so for the sake of Mary, and those that didn't ask, what is that again? Okay, so we are saying, okay, let me just do this. Clinton, can you get me Clinton? Alright, Mary, I'll do that. So Clinton, if you're able to get me, please, after this whole thing, inbox me. Okay, inbox me. If you're able to get me after this thing is over, inbox me. Okay, so for the sake of Mary, we are saying that we are trying to prove that this production function exhibits constant returns to scale. So we know that constant returns to scale implies that if we increase inputs by any amount, let's say Z, then output is also going to increase by that very amount. So that is what we're trying to prove here. Okay, so we're saying that if we increase inputs by Z, then we are saying we are increasing capital by Z. Okay, we're also increasing labor by Z. Then that should be translated to output. So we are saying A, open brackets, let's increase Z, let's increase capital by Z, so it will be Z times capital, close, raise the power alpha. Again, let's do the same with labor. So we're saying Z labor, close, raise the power 1 less alpha. Okay, so if we open the brackets here, who is this? I'm so sorry. Let me just okay, sorry, I'm so sorry. So now, if we open the brackets, we're going to have this thing az raised to the power alpha, k raised to the power alpha, because we're just opening the brackets. These are indices. We did indices in grade 10. Then z raised to the power 1 less alpha, l raised to the power 1 less alpha. So now, we are saying, let's bring the z's together, because these have got like terms. Okay, we've got z here and another z there. Okay? Okay, so so now if we bring the like terms together, we're going to say z raised to the power alpha, again z 1 less alpha, okay, so we are saying it will be z raised to the power alpha, then times z raised to the power 1 less alpha. These like we've got a z here and a z here, so which means these guys are like they have the same, you know, to some extent they have the like terms, which is the z itself. So we are going to group those together. Then you have this thing again. Of course, so I've put something important here. I'm saying use the laws of indices. So just use the laws of indices. We have not yet reached calculus. We're just playing around with indices. So we are saying this then should equal. So we know that from the laws of indices, if the bases are the same, you keep the bases and add the powers. Okay, so we're keeping the base here, which is z. So if we keep the base z, then we add the powers. We've got alpha plus 1 less alpha. Okay, so I've got z raised to the power alpha plus 1 less alpha. Then times this thing, times this. So now, if we do that, alpha plus 1 less alpha, this alpha is positive, that alpha is negative. Okay, which means those ones will cancel. We're just going to remain with z raised to the power 1. But mathematically, we cannot say z raised to the power 1. Okay, so we have got a silent one here. So this is just going to be z times this. Okay, so now, since we increase the inputs by z, okay, we increased input by z, again, our output has also increased by z. Because initially, before anything was done, we had this thing. We had alpha k, we had a k alpha l raised to the power 1 less alpha, which is this part. But now that we have increased inputs by z, output has also increased by z. So now we can conclude that after increasing inputs by z, output has also increased by z. Thus, this Cobb-Douglas function exhibits constant returns to scale, because we've increased inputs by z, output has also increased by z. So this is how we prove that this particular production function exhibits constant returns to scale. So if after plugging in, or if after doing all this that we've done, we find that we have, let's say, a negative z here, then we know that it has got decreasing returns to scale. Okay, if after doing all this that we've done here, we find that the final answer is increasing more than z. Okay, let's say if we had z raised to the power 2, then we're going to conclude that this whole thing has increased more than what was expected. Then this would have said that it exhibits increasing returns to scale. But in this case, we've seen that after increasing inputs by z, output has also increased by z. Thus, we can make a conclusion that the Cobb-Douglas function exhibits constant returns to scale. Okay, so this is how we prove. Okay, anyone with a question, or anyone who is behind, or anyone who wants some form of clarification? Mr. Kaira. Yes, Sandra.
Yes, please. I didn't get the meaning of the alpha. What does it stand for?
Okay, so alpha and 1 less alpha. These two represents the share of income that is paid to each of the factors of production. So since K is raised to the power alpha, then alpha represents the share of income that goes to capital. And then since L is raised to the power 1 less alpha, then 1 less alpha represents the total share of income paid to labor. So that's what these two represent. Okay, Sandra? Uh-oh. Uh-oh.
You said that the share of income that goes to capital?
Yes, the share of income that goes to capital is represented by alpha. The share of income that goes to labor is represented by 1 less alpha. So now, just there, let me explain something. Check this out. Check this out. Since we've got alpha and 1 less alpha, the simplest method that you can use to check if a production function has got decreasing, constant, or increasing returns to scale is to add the alpha plus 1 less alpha. If after adding alpha plus 1 less alpha, you get a number which is less than 1, then this thing it exhibits decreasing returns to scale. If after adding alpha plus 1 less alpha, you get exactly 1, then the production function exhibits constant returns to scale. If after adding alpha plus 1 less alpha, you get a number greater than 1, then it exhibits increasing returns to scale. So that's the simplest method you can use. But when they say prove, you don't go for that one. You have to use what we've used here. Just to play around with indices and then check your final answer. Okay, I believe that is well. So you're saying thus we can see that after increasing the inputs by Z.
Yeah.
Yes, sir. Yes, sir. Yes, sir. Yes, Mr.
Can you edit before you send this document? Yeah, when you are multiplying those brackets, moving the brackets, you forgot to put, is it an AK alpha?
Where? When I was opening.
Later on,
It's AZ alpha, then K alpha. Okay? Then this Z is raised to the power 1 less alpha. Then this A is raised to the power 1 less alpha. There's nothing wrong. Because this A is multiplying with everything. So we cannot say A times this, again A times that. It's the same thing. So this A is multiplying with everything. Because this is just multiplication. So whatever is here, whatever A is multiplying by everything. So if you're talking about this, I believe there's nothing wrong. Mr. Alfred?
Alright, thank you, sir.
Alright. Okay. So we are saying that thus we have seen that after increasing the inputs by Z, okay, output has also increased by Z. Thus we can conclude that the Cobb-Douglas production function exhibits constant returns to scale. So this is how we prove that a given production function has exhibits either decreasing, constant, or increasing returns to scale. Okay, let's feel free, guys. Do we have issues there? Because these are things that will be expected to do in macroeconomics. Everything that we've been doing is first year macroeconomics. This is where second year starts from. Okay, so if you don't get it here, I don't know where you're going to get it from. So if you...
Yes, sir.
Yes, Mary. Mary, your mic was on. I believe you wanted to say something. Okay, I believe that is well.
I have a question.
Yes, feel free.
Yeah, I'm kind of lost.
Okay.
Where you explain, where when multiplying there, could you display the sheet? Okay. So there, where you said that when multiplying, it means that A multiplies with everything there. But I can't get, I can't get it. Why it's only
Why can't you get it, sir?
there, because when you multiply there, it's supposed to be A, Z, then again A, K. but it's only AZ.
No, it's not. It's not only AZ. The only thing that I can see maybe is that I was supposed to put open parenthesis here and closing parenthesis there, just to show that A is multiplying by everything.
Okay, that makes sense.
Okay. But otherwise, even the way it is just okay because this is multiplication. Okay, but I think maybe to clear that issue, I'll try to put some parentheses here before sending the document. Okay, Mr. Panda. Okay, so if that is the only concern, then we can continue. Okay, we can continue. So last time when we were discussing this, we were just talking about marginal product of labor, marginal product of capital theoretically without showing what it is. Okay, so now today, yes sir. Yes sir, I can get. Yes, Mr. Farai, sir.
Can you show again how you show that when you're proving, how you show that it's now showing that you have increasing returns to scale and the diminishing returns to scale?
Okay. So I hope you've understood what this means. So basically, it's just the issue of playing around with indices. So of course, you have to open the brackets there and there. Then you collect the items together. Then you play around with indices, obey the laws of indices. Of course, we know here that Z and Z, these have got the same bases and the base is Z. So you maintain the base, you add the powers. You maintain the base and add the powers. When you do that, this A and that this alpha and that alpha will go. You remain with 1. Anything raised to the power 1 is that same thing. So in this case, is Z raised to the power 1. Then A times this thing. So now, how do you know that I have decreasing, constant, or increasing? If let's assume that the Z we're talking about is 2. Okay, so increase capital by 2, increase labor by 2. And then here, after playing around, after doing all these things, we have a 2 here. Then we're going to conclude that we have constant returns to scale. But if we've increased by 2 there, and then here we have something, let's say 1, then we are going to conclude that after increasing inputs by 2, output has only increased by 1 unit, which means I have decreasing returns to scale. Again, if after increasing inputs by 2, I have a value here greater than 2, let's say 2.5, then I will conclude that this thing has got increasing returns to scale. Mr. Farai, sir, are you clear now?
Yeah, I am.
Okay, we thank God for that. Okay, another question before we leave this part. Believe you me, this is very important. This is very important. Because you'll be given some complicated Cobb-Douglas function where they want you to play around with mathematics first before it comes to something like that. Okay, so this is very important. Let's understand this. It will not make sense if we continue when you still have some issues uncleared here. So feel free. I'm very flexible. Feel free.
Excuse me, sir.
Yes.
Kindly repeat in the same.
Okay.
I'm a bit lost. I'm not understanding what's going on.
All right. Thank you so much for being open. Okay.
Mr. John.
Yes, sir.
Sir.
Any numerical example?
Okay, I'll give you the numeric example. We have examples down there.
Yeah, I think be helpful.
Okay, all right. And please, don't address me as sir. Okay? Matambo. Just feel free to call me Matambo. Not sir, please. Chini Kulila, it's a very big title, that one. So just call me Matambo. Okay, so let me repeat myself. I believe this time around, R will be well. So you're saying that...
I think it would be just better if we look at a numerical example.
Well, that one will just make people a bit lost because it's... Where is it? Though this one we're talking about try to calculate for the distribution of output. Wait, let me just check if I have a proper numeric example based on this. Sorry, let me just check.
All right, Mr. George.
Because I have this document which I prepared last year. So let me just check. No. This one is based on finding the marginal productivities and everything. Okay, so what I'll do is this. What can I do now? Okay, what I'll do is this. Maybe for now, let's try to stick to what we have. Then immediately after this, I'll send a numerical example. Because what I thought was, if you guys are going to understand using letters, then the numeric example will be easy to understand. But since it seems to be the other way around, I'll send a numeric example, because what I thought was, maybe this is going to cater for that. But here we're just calculating for the marginals and the changes in the labor composition and everything. Okay, yeah, this is just some percentage changes and everything. Okay, but don't worry, this time around I'll be very slow. I'll be slow so that we understand this, because this is going to help us tackle those questions that we have. And the questions that I've used, the exam questions that I've used and that I've provided solutions here, these exam standard questions. I've just changed where there is some name. I remember I've put Christopher and everything. Yeah. Okay. So let's just try to understand this. Yes, Sam.
If you are saying that A multiplies everything, why is it? I'm little lost there. Why is it that there is just, instead of AZ, they just D, then AK, alpha, and so on and so on?
Where is that? Where is that? Okay, let me just restart the whole thing so that I clear it. Because right now I don't even know where you're talking about, where it's here or there. So let me start the whole thing step by step.
Okay. I'm saying on the final answer here.
Oh, here.
Yes, since you are saying that A multiplies everything, whereas A disappears, the one with AZ.
At where has it disappeared? Oh, I get you. my dear. 3 times 2 is 6. 2 times 3, the answer is still 6. You understand the logic there? You understand the logic there?
No.
Okay, I'll explain things that I've noted what you're talking about. I'll explain what I mean by that. Okay, so let's restart. So we are saying that if a production function exhibits constant returns to scale, sorry for that. Okay, so you're saying that if a production function exhibits constant returns to scale, okay, then if we increase inputs by any amount, in this case we're saying that that amount that we're using to increase inputs is Z. Okay, is Z. If you have this book, try to use it. Let me just show you the book. It's also good when it comes to explanation of this. Let me just search for it. I don't even know where it's located. Where is that book? ManQ. Just a minute. So as we're waiting for the thing to load, so we are saying that if you increase inputs by an amount Z, then output must also increase by an amount Z. Then we are going to say that this production function exhibits constant returns to scale. Okay. Why is it taking ages? Okay, the book must be this one. So let me just do that. One. Oh, sorry. It will be the 5th edition, if I'm not mistaken. Man, I'm still busy. Okay, so this is a book. So what I'm talking about is this. So are you able to see this? Hello? Just confirm, please, guys. We move.
Yes, we are able.
Okay, so you're saying to prove that the Cobb-Douglas production function has got constant returns to scale, let's examine what happens when we multiply capital and labor by some constant z. Okay, so we are multiplying z by k, then then z times l. Okay, so we are increasing capital and labor by the same amount z. To avoid complication, sorry, let me just turn this thing off. Okay, so now we are saying a. So you see that what I've done is the exact thing that has been done here. So a open brackets z times k, everything raised to the power alpha, times open brackets z l raised to the power 1 less alpha. Okay, then let's open the bracket. So we're saying a times, so this a, get me right, this a is applying to everything there. Okay, don't start separating that a is just multiplying by, let's say, capital or something. No. Okay, so we are saying that this will be a, then z raised to the power alpha, because z raised to the power alpha is z alpha, then k alpha is k alpha. Then we do the same here, z times that, so it will be z raised to the power 1 less alpha, again l raised to the power 1 less alpha. We've opened the brackets. We've opened the brackets, which is this part. Okay, which is this part. Are you there, Mr. Banda? What I've done here is that I've just multiplied. Sorry, I've just opened the brackets, and then this a, of course, is multiplied by everything, just like it is here. So any computation, any manipulation that we're going to make here should not disturb our function. So this a, just like it is here, is multiplying by everything. What I've done here is just opening the brackets. Then of course multiplying. Okay, can I continue? Is everything okay? Okay,
yes, you can continue.
Okay, thank you. So now, after this step, we now bring the like terms together. So what we're going to do is we're just going to collect. Okay, we're just going to collect. Mind you, this a, this is multiplication. That's why I say the 3 times 2 is 6. 2 times 3, the answer is still 6. Okay, so it doesn't really matter which one you start with. Okay, so this will be z. This z and that z must be collected together. Okay, then this a and this can be multiplied in another way. Okay, so we are saying that this will be z raised to the power alpha, again is z raised to the power alpha, 1 less alpha. We've collected the z's together, and then we can now multiply this times the remaining part. So it will be a k alpha l 1 less alpha, which is this part. Okay, so what I've done here is just collecting the like terms together, and then after doing that, so the reason as to why I'm doing all this is to use the laws of indices. Okay, but if you're sharp enough, you can see that this z and that z, they have the same bases, which are the z's. So if you want, you wouldn't even want to go through this process. All you can do is maintaining the z and adding the exponents, so that you come to this step. But to avoid complication, I've done this step by step. Okay, so after doing that, I will just use the laws of indices. The bases are the same. Z and Z, they are sharing the same base. So I will say Z then raised to A plus 1 less alpha. Sorry, alpha plus 1 less alpha. Okay? So, and then I'll have this guy, just the way it is, I'll bring it here. Okay? So this thing is the same as that thing, which is the same as that thing, which is the same as that. What I'm doing, or what I've been doing, is just playing around so that this thing can be simplified. Okay? Now, alpha plus negative alpha is just more like alpha minus alpha.
You're breaking, sir.
I'm breaking. Christopher, just confirm if I'm breaking.
I've been breaking throughout.
Then I'm sure it's your net. Kukenga, I assume it's your net. Okay? I assume it's your net. Because whenever I'm using Zamtel, I don't experience network issues. No. So I assume it's your net. I'm sorry for that. Try to, I don't know if you're inside, try to go outside. If there's a light by the veranda, just go there, you know.
Here now.
Okay. Okay. So, okay. So, what I'm saying is this now. You collect these guys together, okay, and then you apply the laws of indices. The bases are the same, so it will be Z raised to alpha plus 1 less alpha. Now I was saying alpha plus negative alpha. It's just more like you're saying alpha minus alpha. And alpha minus alpha is 0. But you have got this one. So this is more like Z raised to the power 1. Because we are mathematicians. We know that what we have here is just a 1. So this is more like Z raised to the power 1. So Z now raised to the power 1 times everything, it will be this. It will be this. So it will be Z alpha, sorry, Z A, where A is technology, K capital alpha, then L 1 less alpha. Okay? So now, the conclusion that we can make is that since we increased the inputs by ZZ, okay, by Z, output has also increased by Z. Same amount. It didn't change. We don't have a negative here. Okay? So, we are going to conclude that this production function exhibits constant returns to scale. And I'm repeating myself. This thing that we've done here is very important. Very important. Very important. Okay? So, this is how we prove. So, I said that if after doing all this, we get something less than Z, then we're going to say we have got decreasing returns to scale or diminishing returns to scale. If after doing all this, we have a value greater than Z, Z is any number, okay? We have a value greater than Z, then we're going to have increasing returns to scale. So your conclusion will be based on what you have done and your final answer. Okay? So what they'll do is, they'll give you, let's say, 3, 4, 5 production functions, different types, and then they'll ask you to prove each one of them if you have decreasing, constant, or increasing returns to scale. So what you do is this. You just do this and then you are good to go. The only difference is that you will be given numbers. Okay? So I didn't, I thought this would be okay like this. So I didn't bother myself to start using numbers, because the point is, if you understand letters, the numbers will be easy. Okay? So you just play around with algebra. So now, can I continue now? Are we all okay with this part?
Yes, we can continue.
Thank you so much, Mr. Christopher.
Mr. George.
Yes.
Well, I'm still a little bit behind, but I think if we use numbers like digits, I'll be able to understand better. But you can continue for now.
Okay, thank you. What I'll do is I'll prepare something with numbers. I understand. Okay, so if after doing all this, just like we've done, we see that we have Z here, then we have constant returns to scale. Okay, we have constant returns to scale. Maybe Let me just check. Maybe kuma questions we have something of that nature. Do we have something of that nature? No, not this. No. Okay, but I remember it should be 2018 tutorial sheet. They had something of that nature which was trying to prove and everything. Okay, but don't worry, we're going to use numbers soon. I just believe that you guys are not lost. I just believe that you're not lost. Okay? Okay, now, how do we get the marginal productivities? So now, this is where calculus comes in. And now I'm worried. If I'm having issues with indices, I don't know. Then Derek has got something to do. Because I've been told that the next topic is calculus in math. Okay, but let us not worry, guys. Let us not worry. This is nothing. This is nothing. This is nothing. So now, how do we get marginal productivities? So last time we said that a competitive profit maximizing firm is going to continue hiring labor and capital up to a point where the marginal product of that particular input that you are hiring equal to its real price or its factor price. Okay, so that is what we want to prove here. Okay, that is what we want to prove here. Okay, so today we're just trying to prove the assumptions. So the first assumption that we've proved is that of constant returns to scale, which is what is here. The next assumption or the next thing that we want to prove is that of the relationship between marginal product and the real price of the inputs. Okay, so let's start. So given that we have a production function, okay, which in this case a Cobb Douglas production function, which is AK raised to alpha L raised to power 1 less alpha. Okay, and in case you didn't get me right earlier, I said when you add alpha plus 1 less alpha, okay, in this case, if you add alpha plus 1 less alpha, if you get a 1, you have constant returns to scale. If you add alpha plus 1 less alpha, you have something less than 1, you have diminishing returns to scale. If you add alpha plus 1 less alpha, you have something greater than 1, you have increasing returns to scale. So that's the shortest method that you can use to prove. But I am not encouraging anyone to use that one because it's useless. Because even a grade 1 can do that. Okay, what we're expected of doing is this. This is what we're expected of doing. Okay, so now let's go to the marginal productivities. So given that we have got this production function, then the marginal product of labor. Now, from the definition, we defined the marginal product of labor as being the incremental, output. Okay, that we are going to witness after increasing labor by 1 unit. Okay, so that is the marginal productivity of labor. So you're saying that the marginal productivity of labor is the change of this production function due to a change in labor. Okay, so this is what these mean. These are just derivatives. This is the sign of a derivative. Okay, so we are going to differentiate the given production function with respect to labor. That is how we calculate the marginal product of labor. Okay, so if we have any production function, if we've been asked to calculate for the marginal product of labor, what you do is you just differentiate. You find what we call the first derivative of that particular function. Okay, so the first derivative of that particular function will be differentiating that function with respect to labor. Okay, now how do we do that? Okay, so we are saying that if we have this production function, AK alpha L 1 less alpha, for us to get the marginal product of labor, which is the incremental effect of labor after increasing the units of labor by 1 unit, how we get that is by doing this now. So I'm saying that the change in the production function due to change in labor, but of course, this is just y. This is just y. So in other books, you're going to find that they say change in y due to change in labor. It's the same thing, because we say that y is equal to function of capital and labor. So this can be y. So here in other versions, they will put a y. Here they will put a y. It is the same thing. Don't get confused, because don't forget, in mathematics we use relationships. So if I say that y is equal to x, I can say wherever there's x I put y, or wherever there's y I put x. It's the same thing. Okay, so you have that on your minds. So we are saying that the change in this production function due to change in labor will be, so now we know that this is just a linear, this is a linear, not really linear. So let me not say linear. So using the laws of derivatives or the rules of differentiations, we want to calculate the derivative with respect to labor. So which means what we're going to use, what we're going to do is this. Let me write something. Let me write something so that you see what I'm talking about. Let me just try to share a jump file. Just a minute. Okay. So, in that case, we have this. We have A capital raised to the power alpha. Sorry, this is alpha. And then labor raised to the power 1 less alpha. Sorry for that. So to find the derivative, we're just saying change in y due to the change in labor, which should equal, now we know that if I've got something like this, a x raised to the power, let's say b, whatever, this is b. To find the derivative of this, we are going to say a times b. Okay, so saying a times b multiplied by x raised to the power b minus 1. This is the general method that we use when we are differentiating. Sorry, I just love letters. Forgive me for that. I just love letters. So let me put numbers. Now. Let's say we've got a production function or anything which is 7x. It's not a production function, it's just an expression. 7x raised to the power, let's say 2. To find the derivative of this, we're just going to say 14. Okay, the 14 is 7 times 2, because we're saying a times b. Okay, or maybe to avoid issues, let me just do this. So this will be our a in this case is the 7. So we're going to say 7 times 2. Okay, so that is this times this ab. We are following this rule. Then I'm going to multiply everything by my x, just the way it is, my x. Then this x will now be raised to b minus 1. B is 2. So 2 minus 1 is 1. Which means my final answer will be 14x. So this is how we do differentiation. So I'm doing all this because you have not done this with Derek. Okay? So this is why I'm doing this. So now, let's get back to our production function. So we have got this. So how do we find the change in this production function due to the change in L? What we're going to do is this. L is starting from here, going that side. That's our labor. Okay? And then we are differentiating this particular function with respect to labor. Which means we're going to let the A, K the way they are. We're not going to tamper with them. Okay? So which means the change in Y due to the change in labor will be, I'm going to say open, I'll have 1 less alpha, okay, 1 less alpha times, so I have this, which is my B in this case, so it's this, multiplying by A K alpha, so I'll have my A K, sorry, raise the power alpha, like that, okay, then this L, I'll put in here, okay, I'll put it here, then I'll say this thing minus 1, so this is 1 less alpha minus 1, sorry, minus 1, yes, sorry, not A but 1, so this is 1 less alpha minus 1. Now 1 less alpha minus 1 is just the same as this guy and that guy will go, because this is positive, that is negative, which means I'll be left with negative alpha. So L should be raised to the power now negative alpha, which means I have found the derivative. I have found the derivative of y with respect to L. Sorry for the handwriting and everything, it's not my fault. I'm just using a mouse anyway. Okay, so this is how we calculate the derivatives. So now, the derivative of this particular production function with respect to labor is open brackets 1 less alpha close times AK raised to the power alpha, then L raised to the power negative alpha. Why negative alpha? We have reduced this exponent by 1. Okay, which is going to give us negative alpha. So now, this, the change in y due to the change in labor, which is just a change in the production function due to the change in labor, is the marginal product of labor. Okay, is the marginal product of labor. Okay, so let me get back to the document. So that is what I've done here. So the change in the production function with respect to L is 1 less alpha times AK raised to the power alpha, then L raised to the power negative alpha. And then I'm saying use the laws of derivatives or the rules of differentiation. Okay, so this is now my derivative of this particular production function with respect to labor. Okay, with respect to labor. Okay, are we?
Sir.
Yes, Tarsila.
I'm a bit lost.
Okay. I understand.
Me
I understand. So now that is how we calculate the marginal products. Let me get back to the whiteboard. Yes. Uh-oh. I thought someone was about to say something. Okay. So now what I'm saying is this. If you guys remember this thing.
Sir,
Yes.
you should be using, you should be sharing the steps that you've done.
Okay.
Don't skip my steps. We can't understand.
Sorry, I was skipping the steps because I believe we were once in the first year. But let me just now go back to like step by step. So let me use the same production function. Just use the one I know. Okay, so let me just use the same production function. We have this thing. I believe you're writing. Okay, I believe you're writing. So I've got AK alpha. Then I have labor raised to the power 1 minus alpha. Eish. Anyway, yeah, this is what we have. Anyway, it's not my fault. So I've got AK alpha L raised to the power 1 less alpha, which we are saying this is our production function y. Okay, this is our y. So now to find the marginal product, of labor is just the derivative of this function. But this function is that. So what we're going to do is the change in y due to the change in labor is gonna equal. So if you remember, this ax raised to the power b is just abx b less 1. If you understand this, then I believe this differentiating this thing will be easy, because we are using the same principle, no difference whatsoever. Okay, so what we're going to do is we are differentiating this with respect to labor. I believe you're writing. So this will be open. Okay, I'll get my exponent 1 less alpha times a k alpha first. Okay, so I'll multiply this by a k alpha. Now I'm sure someone is wondering why aren't we tampering with capital? We are not differentiating this with respect to capital. Okay, so capital is going to be held constant in this case. Okay, we are holding capital constant. Okay, that is why we've left the alpha and capital the way they are, because we're not differentiating this with respect to technology, which is A or capital. So we're going to leave them the way they are. But we're going to temper with labor, because we're differentiating this with respect to labor. So now this will be 1 less alpha, the exponent of L. We are not dealing with the exponent of capital, no, because we're not dealing with capital, we are dealing with labor. So we're going to play around with the exponent of capital, of labor. Okay, so this will be 1 less alpha this time. Okay, so here, so we have got this 1 less alpha, a capital alpha. Then let's go back to labor. So we are going to say times labor, but this labor is the one we are using to differentiate y. Okay, so you remember there I said that if you have something like a x raised to the power b, differentiating this will be a b, which means I'm multiplying this times this, then x, then this should reduce by 1, so I'll have b minus 1. So let's apply the same rule. So here now I'm going to say let me just do this. Let me open the brackets. The exponent of L, I'll have 1 minus alpha. Okay, this thing, let me put it in brackets. 1 less alpha in small parentheses. These are the brackets, sorry. Then minus 1, I close with a bigger parenthesis. So this is what I'm doing. So now I'll just have to simplify this, which of course if I simplify, I'll have 1 minus alpha, open, close, these are parentheses, then a, I'll leave it the way it is, capital the way it is, raised to the power alpha, then L, but now I've got 1 minus alpha minus 1. This is positive, this is negative. So these two will go. I'm only remaining with the negative alpha. So I'll say L raised to the power negative alpha. Okay, are we together this far? Guys, are we understanding what we're doing?
Yes.
Okay, thank you. Please, I'm happy. Thank you so much. So now that we have this is what we call the marginal product of labor, because we have differentiated this function with respect to labor. So this is the marginal product of labor. These are the parentheses. Okay, so this is now the marginal product of labor. So this is how we calculate the marginal product of labor. So this is what is here. Okay, this is what is here. I skipped some steps because I thought the guys know these things. So this is how I reached here. Now let's continue. This is just the marginal product of labor. What about the marginal product of capital? How do we get the marginal product of capital? So let's go back to our jump file. So we have the same thing, alpha capital raised to the power sorry, not alpha, this is A, sorry, this is A, technology. Then labor raised to the power 1 minus alpha. Now, this was saying must equal y. Now, the change in y due to the change in capital is just going to be, now I'm differentiating with respect to capital, not labor, with respect to capital. Which means in this case, I'm going to assume that this is constant and that one is constant. It's only this guy that is going to change. So I will say alpha that one, times the technology, capital, okay, capital, and then this is, we're going to say, we're going to reduce this by 1. So it will be alpha minus 1. Because I'm differentiating this with respect to capital. Then labor, the way it is, 1 minus alpha. So now this is the marginal product with respect to capital. Are we together, guys?
Yes.
Okay. Thank you. So this is what I have here, where I'm saying alpha, open brackets, A capital, alpha minus 1. So yes, then labor 1 minus alpha. Okay, which is just that. Which is just that. So I'm saying, please take note that this thing called alpha lies between 0 and 1. Okay, take note that alpha is any number between 0 and 1. It could be 0.00001, it could be 1, it could be 9, it could be 0.9, it could be any number between 0 and 1. This then means that alpha lies between 0 and 1. Thus, okay, I'm saying thus, if you add the alpha plus 1 minus alpha, the answer is 1. Okay? So, hence, we've shown that alpha lies between 0 and 1. So, take note that the figures that are going to give you representing alpha and 1 will lie between 0 and 1. So, now, practically, let me do this. Let's say I've got a production function, here's a Cobb-Douglas, which is this. Let's say 2 being the level of technology. Then, let's say capital, raise the power 0.3. There's a point here. Okay, then I have labor raise the power 0.7. You can see that if I add this, I'll get 1. Okay, 0.3 plus 0.7, 30% plus 70% is 100%. So 0.3 plus 0.7 is 1. So this is now in numerical terms. Okay, so now let's try to differentiate this since we have numbers now. So I will say the change in y with respect to the change, let's say in any, so let me say labor will be, so now I'll have my 0.7 because labor is the exponent is 0.7. So I'll say 0.7 times 2. Okay, so which means I'll have 2 times 0.7 multiplying by, then I'll have my capital raise the power 0.3. Okay, that is a 3. And then I'll have my labor, but then 0.7 less 1 is just a negative of 0.3. So the negative 0.3. Then I have differentiated this. Then, we know we are mathematicians. So, what do you get when you multiply 2 by 0.7? Ati? Your net is breaking.
I have a question.
Yes, Kukenga. Kukenga? I didn't get what you were saying. Christopher, are you following?
Yes, Mr. George.
Okay. Mr. Alfred Peary, are you following, sir?
Yes, again.
Okay. Proper then.
What's the after?
What's the what?
After the equal to? Is that alpha after the equal to sign?
Is that alpha?
That alpha after the equal to sign.
After the equal sign?
The equal to sign.
This one? Or this? This is 2. This is 2.
Is that alpha equal to sign?
I'm lost. I don't even know what you're talking about.
Alpha after equal sign.
Okay, after equal sign we have 2, not alpha. This is 2. Sorry, need 2. It's a 2. This is a 2. No, okay, this is a 2.
This yes.
No, it's a 2.
Alpha.
Can someone type that it's a 2, not an alpha? Just type so that our friend is helped. Just type in the message box, please. I'm sorry. Just do that. This is a 2, please. This is a 2. Okay. So we have this. So this is the marginal product with respect to labor. So now, if we play around with this, what we have is this thing 1.4. Then capital raise the power 0.3. These are things that you'll be doing. Trust me. I just want you to understand this. Then negative 0.3. Okay. So you have got 1.4 goes 2 by 0.7. It's 1.4. So 1.4 capital raise the power 0.3 labor raise the power negative 0.3. Then this is your then you have differentiated. You have differentiated the production function with respect to labor. But check this out. You have this is raised to the power 0.3. This is raised to the power negative 0.3. What you can do is you can play around with mathematics. This is nothing but this. Okay, that's why I love math, man. Makes you think. So I've got 1.4. You can open the brackets, a bigger parenthesis, capital SK, over labor. Everything raised to the power 0.3. It's the same thing. So this is the same as that, not different. What I've done is I've just played around with the exponents. Okay, because this is just the inverse. Anything raised to the power negative is the inverse of that, and the inverse of that is labor. Then if labor is the denominator, then it is that thing. So this is how we play around. But don't worry. Even if you leave your answer here, you're still correct. Okay, but if you want, you can just bring it here to show your tutor that you know mathematics. You can just do that. Okay, are we together, guys? Are we together?
Yes, Mr. George.
I have a question.
Yes, sir.
On the previous formula, you were giving us, is it L to the power 1 minus alpha? Is 1 part of the formula, or you were just showing us it? Like an example. The question comes with one.
What? Come again? I didn't get your question.
On the formula, at least in where there is labor there, you were including, is it 1 minus alpha?
Where?
L to the power minus alpha.
Yes. 1 minus alpha. Oh, you mean the marginal product with respect to capital?
Yes, we are including the 1 minus alpha, but when you were solving from the previous example, you should have just included numbers. You didn't include the power 1 to the labor.
Yeah. Okay. So what it is this, my friend, my friend. What it is this. Here we are differentiating with respect to capital. Okay. Here we are differentiating with respect to capital. So check this out. Where is that thing? This is the production function that we have. So 1 minus alpha is embedded in the function itself, because this is how a typical Cobb-Douglas function looks like. So 1 less alpha is embedded in there. It is part of the part of the formula. Okay, so that is why when I was differentiating with respect to capital, I let it the way it is, because I'm not differentiating with respect to labor. I'm differentiating with respect to capital, which means the only exponent that I can play around with is that of capital. That's why I've got I've got alpha minus 1 here, because I'm differentiating this with respect to capital. I don't know who asked the question. Okay, so are you now clear? Hello?
Yes.
Oh, okay. Thank you. Another question, please. Another question? Is it here, there, or there? Okay, so I'm sure by now you see why using letters makes things easy. Okay, because the moment you understand letters, numbers are nothing, guys. Numbers are nothing. Okay, so that is how we calculate the marginal product of labor and the marginal product of capital. Can I continue? What's the time? 24 past 8. Hey. Okay. Okay, so can I continue? I just want us to look at one example, just one example, because the example has
Yes, you can continue, Mr. Judge.
Thank you so much. Thank you so much. Okay, so that is how we calculate this. So we are saying that from above computations, we note the following. Okay, so from what we've been doing, we note the following. Increasing the amount of capital increases the marginal product of labor, while reduces the marginal product of capital. So what I'm saying is this. Since we have got this type of a production function, okay, since I've got this type of a production function, if I increase the amount of capital, for example, you have got one factory and 10 workers, okay, if you increase the amount of factories to 2, okay, initially you had 1, now we have 2, then that is going to increase the marginal product of labor, because people will have enough space to work on. So the marginal product of labor is going to increase, but the marginal product of capital is going to decrease. Why? You have increased capital. Okay, so capital, the marginal product of capital is not going to increase, instead it's going to reduce. Okay, because what you've done is you've just provided a conducive environment for the workers to work on, which means the labor productivity is going to increase, while the marginal product of capital is going to reduce. So now, these 3 points are what our questions are trying to prove. The examples. Okay, so by now, I think you just get them by faith. Okay, that if we increase the amount of capital, okay, we are going to increase the marginal product of labor, but we are going to reduce the marginal product of capital. So, with the numeric examples that I have, we are going to prove this. Okay, I'll be happy if we're just going to at least prove one of these assumptions, or prove one of these. Then I'll be the happiest person. I'm going to sleep happy. Okay. Then the second one you're saying, if we increase the amount of labor, okay, we are going to increase the marginal product of capital, while reducing the marginal product of labor. So what you are seeing here is that if you increase labor, there will be a negative relationship between the increase in labor and the effect on the marginal product of labor. Okay, so if you increase the amount of labor from 10 to 11, you are just, in simple terms, it's more like you are saying the factory needs more workers. So which means the marginal product of the factory is going to increase, because now it's going to be used to its to the fullest. But the marginal product of labor, since you have increased the labor, people will now maybe start fighting amongst themselves, because with more numbers comes more confusion. So the marginal product of labor is going to reduce, because you have increased the marginal product of labor, but the marginal product of capital is going to increase. Okay, so there is that negative relationship between that particular factor that you're increasing and its marginal productivity. So if you increase labor, the marginal product of labor is going to reduce, but the marginal product of capital is going to increase. If you increase capital, then the marginal product of capital is going to reduce, while the marginal product of labor is going to increase. So just get these, understand these. Okay, for now, take them by faith. We are going to prove them. Okay, I'm going to prove them. So now, the last one is saying, if we increase the level of technology, then we're going to increase the marginal productivities of both capital and labor. Now, this one is very practical. Okay, if you increase the level of technology, then output is going to increase, no doubt about it. Okay, because you are increasing the efficiency of production, you are increasing technology. If you increase technology, then people find it easy to work. Okay, even the machines that we're using, you have higher productivity now that there's this new technology that you have introduced. Okay, so if you increase technology, the whole production function is going to increase. But if you increase one factor of production, the marginal product of that particular factor that you've increased is going to reduce. Okay? So just if you're able to understand them before you look at the numerical examples. But if you're finding it difficult to understand this, don't worry. We have got numerical examples that are going to help us understand this. Okay? So the first one is that if you increase the amount of capital, then the marginal product of labor is the one that is going to increase. But the marginal product of capital is going to reduce. Again, if you increase the amount of labor, the marginal product of those bantu is going to reduce. Okay, because maybe they'll start getting into each other's way and everything, so the marginal product of labor is going to reduce, but capital is going to be fully utilized. Okay, so the marginal product of capital in that case is going to increase. But if you increase the level of technology, which is A, then production is going to increase. Okay, so the whole production function is going to increase. So total output is going to increase. So we know how to calculate marginal product of labor from the examples that we've looked at, which is just this. Okay, so don't get confused. This is equal to that. What I've done is, since this is capital is raised to the power alpha, the labor is raised to the power negative alpha, which is just the inverse. So I will say capital over labor raised to the power alpha. So this is equal to that. Okay, this is equal to that. Again, marginal product of capital is this, which I can also play around. If you play around with indices, you are going to get back. You are going to find that this is your final answer. Okay, so now we have this guy. So this is the one that is the inverse in this case. So you're just going to say labor over capital raised to the power 1 minus alpha. Okay, so if you're finding it difficult to reach here, well, you can end it there, but there are some questions that will ask you to find this. They'll give you a production function and say, prove that it is that when you find the marginal product of labor, it's going to give you this. So you just have to know how to play around with the indices. It's just a matter of indices and some form of calculus, which is this is basic calculus. This is just basic calculus. Okay, but I understand if you're having issues because you have not yet covered this topic in Math 1, which is the next topic in Math 1. So don't worry, we are going to understand these things as you do them in Math 1. Okay, so if we are having issues, don't worry, I'm very much flexible. With the moment you do calculus in Math 1, the moment we do calculus in Math 1, then if there will be need, then you will have to come back and discuss this. Okay, so don't worry. Okay, so this is how we play around with mathematics. So this can be simplified that the marginal product of labor, of course, let me not confuse you because I
So,
did. Yes. Oh yes, ma'am. Oh yes, madam. Sorry.
can we? I'm going to.
Can we? Wait, let me
Can
see.
we end here, sir? We are going to get more confused.
Oh my god. Okay. Don't get confused. Yes, there's need to come back. Okay, we'll come back to this. Okay. Yeah, I don't know. I'm just in the mood of math today. I'm sorry. This is a blow now. Okay. Let's end here. But I wanted us to at least do answer some of these questions. Okay, so before we end this, let's answer the first simple question. Because it's simple. So, yes.
I don't know if my thinking is okay, but I was thinking if we end here so that we pass through, then answering the question would be easy next time.
I understand, but the first question of our example is what we've already covered, and we have understood that part. So I just want you, before we end this, at least to have an understanding of how questions come and how to answer them, particularly on that particular point that we have already covered. So just
please.
Hey.
Don't forget to send the notes so that we go through.
Okay, I'll send them. I'll send it. So I was saying, suppose that Christopher Mulenga, a farmer from Northern Province, uses a Cobb-Douglas production function with a parameter alpha is equal to 0.3. So just from the question, we are able to tell that this is a Cobb-Douglas because we have got this parameter alpha. Okay, so it's a Cobb-Douglas function that Christopher is using, of course, with parameter of alpha equal to 0.3. So the first question is, what fraction of income do capital and labor receive? So what fraction of income do capital and labor receive? So we know that this is just a Cobb-Douglas function of this form. So in this case, they wanted us to first come up with a production function. Okay, so they will just give you one parameter, and then they expect us now to come up with a production function. So we're saying that the function of capital labor is just A, K, alpha, L, 1 less alpha, the normal one. So we know that they have told us that alpha is 0.3. So we're just going to replace A, K, alpha is 0.3 because alpha is 0.3. And then we know that when we add alpha plus 1 minus alpha, the answer must be 1. So if we have 0.3, then here we should have a 0.7, because if I add these two, I will get 1. So we are saying that to answer the question, thus alpha is equal to 0.3, then capital receives 30% of total income. Then 1 minus alpha is 1 minus 0.3, which is 0.7, then capital receives 70% of total income. So this is how we answer this question. Okay, this is how.
Isn't that supposed to be labor receive 70%?
Then I've swapped it there.
Isn't it supposed to be labor receive 70%?
Oh, I have capital and capital there. Sorry, this should be labor, not capital. This should be labor. Because there's capital already there. So this was just an error when I was writing. So capital 30%, then labor 70%. So you can tell from the production function itself. You can tell that capital receives 30%, then labor receives 70%. Thanks for that. So please take note. There should be capital here, and then there should be labor here. Okay.
Before we go any further, how did you find 0.7? Explain on that.
Oh, okay. So there is that point that I said that if you add the alpha and the 1 minus alpha, the answer must equal 1. Even just from here, you can say that if you add the alpha plus 1 minus, in short, if you add the exponents, you must get a 1. Okay, if you add the exponents, you must get a 1. So alpha, we've been told from the question that alpha is 0.3. So if alpha is 0.3, then 1 minus alpha should be 0.7. So that is how I have found 0.7. Because if you add 0.3 plus 0.7, the answer is 1. Okay?
So what you mean is constant tensor scale?
Yes, I've got constant tensor scale. Perfect. We have constant tensor scale. Okay? Can we end now? I believe we can, isn't it?
I have a question.
Yes. Just start with the second question, then you can end.
Okay, I love that. Yes, Kukenga.
I have a question. Can you please scroll up on your sheet? I can't see the screen.
Really? You can't see the screen?
Scroll up. Go up.
I'm still going. Should I continue going
Go
up?
Again, just there.
Okay.
No, calm down.
Here.
Again.
Here.
Yes. There where you have marginal marginal product of labor.
Yes.
You have 1 minus alpha y over k. Then again you have marginal product of capital, which is alpha y over k. So
yes.
It's confusing. Which one is for? How come we have k on both?
How come? Oh, don't know, man. I was making these funny mistakes. Sorry. So this is y over k. This is y over l. There should be an l here. Okay. So this is the y over k. Yes. Then here we should have an l. Here we should have an l. Okay. But of course, don't use because this one.
Where should we have L?
Here, where you have marginal product of capital, it's opposite. Where you have marginal product of labor, it should be y over k. Where you have marginal product of capital, you should have y over l. It's opposite. So here, you should have an l. Here, an l. Okay. Of course, you are only going to get these if you simplify these. But you are getting confused, Kavidi. So I can't even show how I've reached this stage. I think we should just wait for Derek to help you with calculus. I'll tell him to start from indices. Yeah.
So at least an idea.
Yeah, but at least now that. But anyway, it's okay. You have an idea now. So that even when D is explaining that part, we are going to find it easy to understand. But I thought we looked at this in first year. That's why I had no issues. Okay, someone was saying we look at the second question. I'm happy with that. I'm okay. We can go on and on and on. Okay, the second question is just saying, suppose that the immigration raises labor by 10%, which means we have now an increase in labor. Okay, so now we are trying to answer this point B. We are saying that if we increase labor, then the marginal product of capital is going to increase while the marginal product of labor is going to reduce. So we are trying to prove that. Here, we are trying to prove that. So we are saying, suppose that the immigration raises labor by 10%, what happens to the total output, real price of capital, and the real wage in percentage, or in percentages. So, but you're going to get confused here. I can see already that the people are getting confused. So, I don't think so. I don't think we should go ahead with it. I don't know. What's your take?
You can just do it the other day.
Okay, Mr. Banda. Thank you so much. Okay, okay, but understand, before you go, this is now intermediate macroeconomics. Okay? This is intermediate macroeconomics. And these are the questions Mr. Banda loves to bring. Trust me. So, we just have to work together. We just have to work together if we want to pass this course. We just have to work together, trust me. These are the questions that Mr. Banda loves. Okay? So please, Napapata, let's work together. Let's work together. Just a minute. Let me just show you what I mean by that. Banda loves calculations. So his questions are mostly. So you see, this came in our. This take-home test should be 2. Yes, take-home test 2. It came. The Cobb Douglas came, but it came in 3 variables: capital, labor, and the human capital. Okay, so you see, they're saying derive an expression for the marginal product of labor. So we now know how to get the marginal product of labor, which means we can just differentiate this with respect to labor. Then we are off to go. So what I'm trying to say is, this is where macroeconomics intermediate starts from. So don't worry if you didn't understand. It's okay. It's fine. We are going to repeat so that we are all on the same pace at the end of the day. So don't worry. But please take your time to go through. Take your time to go through what we've covered. But don't worry. We are going to understand this. We are going to work as a team. Okay? So don't worry. We are going to work as a team. We are going to understand these things. So the next session is on Sunday. I just don't know because I don't have the timetable as for now, so I don't even know what's there on Sunday. But I'd love us to do this on Sunday, to continue with this, or to restart anyway, so that everyone is happy at the end of the day. So yes, okay, I think we can go. Unless there's some consensus. Yes, Mr. Alfred.
After we are done with this topic, can you make just one session whereby we answer the questions from that rest?
Well, that can happen. It's okay. I'm okay with that. I love calculations, so it's fine. It's fine. It's very much fine.
All right, thank you.
Cooking wanted to say something. Huh? Cooking, I didn't get what you said. Memory, are you there, my sister? How are you? Okay. So yes, so we can go if there are no concerns. We can go if there are no concerns.
So the next session is on Sunday?
Yeah, I just have to confirm with the timetable. I don't know what's there. I don't know what's on Sunday. You know? I don't know what's...
Please share the question on the group.
I'll just share the same document so that you don't have issues. So go through it, and we are going to resume, I think, on Sunday. If not on Sunday, then I don't know, maybe on Monday. I don't know when macro is. This whole thing of changing timetables, there's no kudala muntu. This one I don't know it. But if you guys want us to continue with macro on Sunday, it's okay. I'm okay with that. We're just going to look at these simple calculations. Those simple calculations, these ones. But please go through some form of calculus. Go through some form of calculus, because macroeconomics is just mathematical from the word go. It's mathematical throughout, and the calculus is widely used, and some form of indices. So guys, thank to God, but don't forget to study. Those that are in school, please make use of the leap. Those that are at home, like myself, we can sleep, then 0-0, we wake up till 6 tomorrow. We keep on pushing. Okay? But trust me, next time, I'll be very strict when it comes to admission. I'll be very strict, because some of the people, we've tried to inbox them, they're just leaving us on scene. So we are also going to be leaving them on scene, just like that. It's a two-way issue. It's a linear relationship. So if you didn't pay, just we can talk. We are human beings. We understand. Just inbox us. Give us your manifesto. Skeleton, do you want to tell me something personal?